So, very good evening to everyone, and welcome to the NPTEL's 11th live interactive session on the course Mechanical Behavior of Materials, Part 1. The course instructor for this course are Dr. Shashank Sekhar and Dr. Sudhanshu Sekhar Singh from the Department of Material Science and Engineering at IIT Kanpur. And myself, Shubham Jaiswal, I am a research scholar in the Department of Material Science and Engineering at IIT Kanpur. So in this live interactive session, we will be going to solve some concept related problems, which will in turn will help you to solve your weekly assignments. So in today's live session, we'll first discuss, means quickly recapitulate what are the things has been covered in the week 11. Then we'll solve, this time we will solve assignment 11. As yesterday we didn't had sufficient time, so we didn't solve it. So today we'll solve assignment 11, and if the time permits, we'll try to discuss some more concept related problems. So let's begin. So week 11, we begin with the concept called strain hardening. So what is strain hardening? So suppose if we induce a strain in a material, then what will happen? These strains will cause dislocation to generate inside a material, and as these dislocations are getting generated, then these dislocations will interact with each other, and they will result in the increase in strength of the material. So let me write down. And then dislocations interact with each other, and hence strength increases. Okay, so this is how we get the strain hardening effect inside a material. So after that, we have seen the single crystal deformation, how the single crystal deforms. So let's say this is my single crystal subjected to stress, some sigma. Okay, so inside this single crystal there are several slip systems and several planes are there. Okay, this is my one plane. So parallel to this, there are many planes will be there. Let's say this is my some second plane, and parallel to this, some more planes are there. Okay, so what will happen in this case? The multiple slip systems are there, but as we increase the load, so the result shear stress in some, let's say some in one plane which reaches the critical value. So what will happen? It will start deforming, means dislocation will start to move. So and as again we increase the stress, so CRSS on other slip plane will also be get reached, and what will happen? These dislocations will also try to move, and then this dislocation will interact with each other, and then that will lead to the strengthening of the material. So we have multiple slip systems Then we have, so as load increases, the result shear stress on one plane reaches critical value. So if we reach the critical value, what will happen? So the dislocation will start to move. So dislocation starts to move. So on further increasing the stress, what will happen? The CRSS on other slip systems will also be reached. So CRSS, so CRSS on other slip systems also reached. So these dislocations will again start to move, and then as more dislocations are moving, so these dislocations interact with each other and results in and lead to the strengthening. So this is about the single crystal deformation. So if we plot the shear stress versus shear strain curve for the single crystal, so we will get the shear curve something like this. Okay, so let's say here we are getting 3 zones. So here we are getting almost 3 zones, and here somewhere we have the transition zone. Okay, so this is the first zone. Let's say this is our second zone, and this one our third zone. So in this case, the first zone is known as the easy glide. Why? Because the slip system with the lowest CRSS will get activated, or in the other word, we can say the slip system with the highest humid factor will gets activated first. So and what will happen? And it will show the negligible strain hardening as the dislocation slips away. Okay, so here you can see as the only some small dislocations are there. So in this region here, I am marking with the blue. So in this region, okay, so dislocations, as the number of dislocations are very less, means the slip system with the lowest CRSS will get activated first. So the dislocations will easily glide away, and we can see the negligible strain hardening effect due to the dislocation. So, but in the second zone, that is the strain hardening. So, what happens? More than one slip systems get activated. Okay, means in more than one slip system, that critical result shear stress value has been already been reached. So, more dislocations will starts moving, and this dislocation then will interact with each other, and it will give the strain hardening effect. So in this case, we can see almost linear strain hardening effect is been observed, and the main mechanism in the strain hardening in the second region is due to the pile up of dislocation. So the stress and strain field of the dislocations will interact with each other, and that will result in the piling up of the dislocation. And similarly, these dislocations will tangle with each other, and they will form the cell structure. So let me write down for the first stage, that is the stage 1, that is easy glide. So in easy glide, slip system with lowest shear resistance gets activated, that is with the higher Schmidt factor, and that is, we can say that we get negligible strain hardening as all dislocations moves away. Okay, so this is about the easy glide. The second stage, that is the strain hardening. So in this, more than one slip system becomes active and dislocations interact with each other and almost linear strain hardening is observed. Okay. So almost linear strain hardening is observed, and the main mechanism of strengthening is pile up of dislocation. Then the dislocations tangles with each other and they form the cell structure. Okay. Then the third was that is step in this curve, the third region is the known as dynamic recovery. So what happened in this region? It is generally characterized by the decreasing rate of strain hardening, and the what will happen? The cross slip will takes place, and it will release the stress due to the pilot. So and dislocations will move. So dynamic recovery. So cross slip start to take place and releases the stress due to piling. Okay, so this is the thing about the deformation in single crystal. So if we see the deformation in polycrystalline material, deformation in polycrystalline material. So if I plot, we'll get curve something like this. So here we get only second and third stage. That is, first stage is missing. So what will happen? So in case of single crystal, only one crystal is there. I mean, only one grain is there. But if we talk about the polycrystalline material, so there are number of grains are there inside that material. So what will happen? So if suppose this one grain starts deforming, okay, so the another grain should also start deforming. If not, so what will happen? It will lead to the discontinuity and it will create the void. So this is how the material will deform. So in case of the polycrystalline material, so as there is no easy glide, means as there is not one set of a plane at a time can deform. So that's why the easy glide is means the stage of easy glide is missing here. So directly we see the stage 2 and stage 3. So let me write down. And again, so if only one set of cannot deform, as this will lead to discontinuity and voids. And again, so if you need to maintain this continuity, so the minimum number of slip systems require, independent slip systems are required, are two in case of the 2D material, and in case of the 3D, we require minimum 5 numbers of independent slip systems. So minimum independent slip system required to maintain continuity are, in case of 2D it is 2, and in case of 3D it is 5. Okay, so this is about the deformation in polycrystalline material. So then after this we have seen the concept known as Taylor hardening. So the Taylor hardening gives the relation between the shear stress of the material and dislocation density. So let's say if we have a dislocation, these two dislocations, okay, sitting at a distance x and y, okay, so the force in this case is given as shear stress into B, that is GB upon 2 pi 1 minus mu into b into ax into x square minus y square divided by x square plus y square whole square. Okay, and if we are considering it is in the same glide plane, and then the stress, okay, then the stress is given by critical given by GB upon, sorry, sorry. So this is the force on a dislocation. So if we plot a curve like how the force is acting, so here on x-axis or x in terms of y, and here we have the force. So if we plot, okay, let me mark these two lines as well. So here we have 1y minus 1y, here we have plus 1y, 2y, 3y, minus 2y, minus 3y. So we'll get a curve something like this. So here it will have the maximum value, okay, we'll get a curve something like this. Okay, so if we see if the dislocations need to be moved, it should cross the this value. Okay, this is the maximum force. Okay, and it occurs at distance of 0.414 y, so minus 0.414 y. So maximum and minimum, so both are only the change of sign. So in this case, if we put this value, that is minus 0.414 in this equation, so we'll get the critical shear stress as GB upon 8 pi 1 minus mu into 1 upon y. Okay, so this is the critical shear stress that a dislocation need to overcome if he wants to move. So now let's say if I have a dislocation, and the distance between the dislocation is given by, let's say, the h, and this is also, let's say, this is also h. So if we consider some area like this one, the one I am marking in the blue, so it will have the length 2h and okay. So if we find out the density of the dislocation in this area, so we'll get how many dislocations are there in this case. This one is 1, and 1 by 4th of all 4 dislocation. So it will get total 2 dislocation divided by its area is how much? It's 2h square. So if we solve it, we'll get 1 upon 2h square, or we can say that the distance between dislocation is nothing but 1 upon root 2 into dislocation density. And if we put this value of h in our equation, the equation that we got here in this equation, so we'll get tau naught is equal to alpha gb into rho. So this is the expression for Taylor hardening. So it gives the shear strength of the material as the function of dislocation density. So as function of dislocation density. Okay. So if I plot the graph, okay. So let's say I have deformed the material. Okay. So let's say this is my yield point 1. Okay. Means this is my yield strength 1. Okay. So after some deformation, I have released it. Okay. Let's say I have deformed it till this point, and then I have unloaded it. So when I am loading it again, so this will be my yield strength. So yield strength 2. So you can see that this much increase in yield strength has been observed. So if we plot, that is the shear strength of the material with respect to dislocation density. So B rho and here tau by G. So we'll get this linear relation that with increase in the dislocation density, the strength of the material is increasing. So this is all about the Taylor hardening. Then in strain hardening, we said that the dislocations will get interact with each other. So how these dislocations are generating? So for that we have seen the concept of dislocation multiplication. Okay. So in this mechanism, first mechanism that we have seen was the Frank Reed mechanism. So what does Frank Reed mechanism tells us? Let's say Okay. So let's say the dislocation is pinned in between these two blue points, and I am applying some shear stress. So what will happen? This shear stress will cause this dislocation to bow, and it will try to increase its length. So this will result in the bowing of the dislocation. On further applications, what will happen? So it will take a shape something like this. Okay, means it's increasing its length. Sorry. Okay, and one point comes when this dislocation will get a shape something like this, and here you can see this is the direction of Burgess vector. So these two opposite dislocations will annihilate with each other and will get a dislocation here. So this is the Frank-Reed mechanism. So how dislocations are getting generated. So here in this case, so as we increase the stress, the density of the dislocation is increasing. So we have seen in one video in which animation. So as we are increasing the stress, the number of dislocations is getting increased. It means the dislocation density is getting increased. And from the stellar hardening, we know as the rho increases, the shear strength of the material will also increase. Okay. And again, also the dislocation pile up leads to strength. So here one dislocation is generated. Then after that, again dislocations are getting generated here. The one that I have shown in the green. Then again some dislocations will get generated, and it will get at the, and it will start piling up, and this will result in the increase in strength of the material. So this is about the Frank-Reed mechanism. So there are other mechanisms for the dislocation multiplication. So what are those? The first one is nothing but the, if the due to the accidents in the crystal growth, we'll get a dislocation. So due to crystal growth from the made. Okay. This is one mechanism. The other mechanism is the homogeneous nucleation of dislocation. And the third one is the stress concentration that is taking place in the inside the material will also aid in the dislocation multiplication. dislocation multiplication. So this is about about the mechanism of dislocation multiplication. Then after that we have seen so how these dislocations are interact with each other and how they are contributing in the increase in the strength of the material. So let's dislocation interaction. So we say that the when two dislocations intersect with each other and it will leave a jog or king behind. So when two dislocations interact, it will leave a jog or king behind. So as this jog and king are nothing but the extra segment, so it will require some energy. So for formation, so the extra work done needed to be done by the external forces, and hence it is resulting in the increase in the strength of the material. So as this extra segment require energy, hence work done by external force is needed and it will result in the hardening of material. So let's say this is my one dislocation and either I am getting formed, it is kink or jog, so its length is increasing. So if the energy per unit length of the dislocation is given by alpha GB square, and if I want to find out the density for the energy for the this newly formed step, so it will be equal to E alpha GB cube. So this much energy is required for adding a step in a dislocation. So if this much energy is required for adding a step, so it means the external force that we are applying should do the more work done. So if it is doing more work done, it means it is hardening the material. So this is about the dislocation interaction. So we'll see like how different dislocations will interact with each other. So here we need to remember one thing, that the steps formed in dislocation 1 will be parallel to Burgess vector of dislocation 2, and its size or the magnitude will be equal to the magnitude of second Burgess vector. So steps formed in this location 1 will be parallel to Burgess vector of dislocation 2, and its size will be equal to magnitude of Burgess vector of 2. Okay, so these are the things we have seen in the dislocation interaction. So now if we consider the first case, that is the two edge dislocations interacting with each other and their Burgess vector is perpendicular. So let's say the case 1. Let's say the case 1, that is two edge dislocations and their Burgess vector are perpendicular. So let me draw the plane for you. So let's say these are my two planes. So let's say this is my first edge dislocation and it is having Burgess vector B1 in downward direction, and the second dislocation, let's say here I am having my second edge dislocation and here I have the direction. In this direction it is moving. Okay, so according to the procedure, that is the steps found in dislocation 1 will be parallel to the Burgess vector of dislocation 2. So if we draw, so what we will get? Okay, let's say this is my plane of intersection. Okay, so what will happen? This dislocation 1, it's moving downwards. So for dislocation 2, the steps 1 will be formed in the direction of Burgess vector. So we'll get a step somewhere like this, and it will be on the some other plane. So it will be on this plane. Okay. Okay, and let's say this is Burgess vector B2. So, and if we plot for this one, so this one will shift somewhere here. So let's say this is my S1 step 1 and this is my step 2, and this is my direction of Burgess vector. Okay, B1. So in this case we know that that S2 is perpendicular to B2 and S1 is perpendicular to B1, and the magnitude of S2 is equal to Burgess vector B1 and magnitude of S1 is equal to magnitude of Burgess vector 2. So in this case, as you can see here, both the things are changing the plane. So both these steps are of nature. So it will form a job. Okay. This was the case 1. The case 2 was two edge dislocation and their Burgess vector are parallel to each other. Edge dislocations and Burgess vector parallel. Okay. So if I draw, so let's say these are the two planes. And let's say this is my Burgess vector 1 and it is moving in this direction B1, and let's say this is my dislocation. This is my dislocation 2 and it is moving in this direction. Okay, so this is the condition of two edge dislocation and their Burgess vector are parallel. So how these two will intersect? So okay, so here you can see this Burgess vector 1 will create a steps in a second dislocation. So if this is my line, so you can see that the step is being created in the dislocation 2. Let's say this is S2, and this dislocation will create a step in the Burgess vector B1 and it will be equal to and these steps will be in the same plane. So these two steps are in the same plane. Okay, so it is not changing the plane. So it means this S1 and S2 are the kinks. So S1 and S2 are kinks, and as in these two cases, the Burgess vector is parallel to the steps. So it means these kinks are in screw in nature. So screw. So this is the case 2 where the 2 is dislocation and Burgess vector intersect. The third case that we have seen was the case 3 that we have seen was the one edge dislocation and one screw dislocation. So edge dislocation and screw dislocation. So let me draw the figure first. Okay, so let's say this is my one screw dislocation. This is the direction of my Burgess vector B2, and let's say I have one edge dislocation here. So its Burgess vector is B1 and in this direction. So how these two dislocations will interact with each other? So here, drawing again. So as this Burgess vector is moving this side, so it will create a step in B2 in the direction of B1. So we'll get something like this. So we'll get some step something like this. And let's say this is my step S2 and this is my Burgess vector B2. And similarly, when the Burgess vector 2 intersect with the Burgess vector 1, it will create a step in this one. In this one. Sorry, let me change the color. So, in this case, it will change the plane. Okay, so it will be in the new plane. So the new plane will be somewhere here like this. Okay, just visualize. So in both the cases, both the steps are changing the slip plane. So this both the dislocations are means both the steps are jog, and here you can see that both the jogs have a edge character as their Burgess vector is perpendicular to their line vector. So next, the third case, the fourth case that sorry guys, the fourth case that we have seen was when two screw dislocations interact with each other. So, two screw dislocations. Let me draw the plane for you. So let's say I have one screw dislocation here. This is the direction of Burgess vector B1, and I have the second dislocations, screw dislocation here. And its direction is here. Let's say this is the Burgess vector 2. So if these two dislocations will interact with each other, so how it will form the steps, and what will be the nature of that steps, we'll see. So let's say this Burgess vector 1, means dislocation 1 interacts with the dislocation 2, so it will create a steps in the direction of B1. So if I see this, so this is my S2, and this is the direction of Burgess vector. And when it intersect with the second one, the second dislocation, so how it will create? So it will create a step something like this. So now tell me the nature of these two different segments, S1 and S2. This kink is as this dislocation 2 S2 is creating the steps in the same plane. So this is our kink, and here this dislocation 1 is creating the step and it's changing its plane. So this sorry guys, this segment 1 is being created and it is changing its slip plane. So this segment S1 is nothing but a jog, and this kink was of nature edge, and this jog is of also the nature of this jog is also edge. So this is how the different dislocations will interact with each other. So then after this we have seen the concept of dislocation locks. So and in that also particularly we have seen the Lamore Cottrell lock in FCC. So let's say I have a two plane. Let me draw. So let's say I have two plane. One is the 1 1 1 in FCC and one is the bar 1 1 1. Okay. So in this plane, there is one dislocation. Okay. So in 1 1 1 1, let's say it is 1 bar 2 bar 1 1 0 type, and here it is A by 2 1 0 1 bar. So in case of FCC, we have seen that this perfect dislocation will separate into two partial Shockley partial dislocations. Okay, because they are energetically favorable. So let's say these two dislocations are being created on this plane. Okay. So let's say here also this is another dislocation and this is one more dislocation. So let me write down. These are the partial dislocation, and this partial dislocation will create a stacking fault. Okay. So what will happen when this dislocation will move? So let's say that the dislocation orange one will react with the blue dislocation. So it will create a dislocation, a new dislocation. Okay. Like this black one. Okay. New dislocation. Okay. So and the line vector of this dislocation will be the cross product of these two planes. So it comes out to be 0 1 1 bar. And if this is the line vector and the Burgers vector, and if we calculate the slip plane for this dislocation, so it comes out something other than that of the FCC strip system. Means that is given in the FCC strip systems. Like for the FCC, we have the 1 1 1 plane, but the plane for this dislocations is other than the 1 1 1 plane. So this dislocation will be very difficult to move, and it will result in the piling up of further dislocations, and hence it will increase the strength of the material. So this was about the dislocation logs. Then we have seen the concept of strain aging. Okay, so it is generally observed in the medium carbon steel. Sorry. So let's say I have a stress strain curve, something like this. Okay. Okay. So in this case, this is the yield strength, and here we have seen the yield point phenomenon. So if I load it till this point, okay, that the blue one, and then I unload it, so I will get unloading curve, something like this. And if I again reload it, so it will follow this blue line and it will give the strength like this. Okay, this blue one. Okay, so this is the case when we do not hit the material. So this is the without hitting. And if we hit the material, so what will happen? So the atom will diffuse to the dislocation core, and again it will create the quadral atmosphere, and we'll get the yield point phenomenon. So let's say this is my case after hitting. So the combination of strain hardening and aging is nothing but the strain aging. So this is the case of after heating. So what is happening here? Yield point phenomena is reappears. And why it is reappearing? So it is reappearing because the solute atoms will diffuse to the dislocation core and it will create the quadral atmosphere, and that's why we are getting this yield point phenomena. So it happens because solute atoms diffuse to dislocation core and again show yield point phenomena. So this much things we have covered in the last week. So now any doubt till this point? Otherwise we'll move to solve assignment 11. Okay. So let's come to the assignment 11. So here is the first question. So in an FCC metal, a pure S dislocation D1 with a Burgess vector B1 on 1 bar 1 plane intersect with a pure S dislocation D2 having Burgess vector B2 on a 1 1 1 plane. The following are true. So 4 options are given and they are asking the nature of S1 and S2, whether it is king or screw, and their character, whether it is H character or screw character. So please try to answer these guys. Please try to answer this. First, you need to check the Burgess vector, whether this is perpendicular or parallel. Then try to draw the plane with containing the Burgess vector. Then use the concept that is the step form in dislocation 1 will be parallel to Burgess vector of dislocation 2 and its size will be equal to that of the dislocation, the Burgess vector of that dislocation 2. So let me write down the concept for you that steps form in dislocation 1 will be parallel to Burgess vector of dislocation 2 and its size will be equal to magnitude of second Burgess vector. Okay. So here, if we observe these two Burgess vector B1 and B2, both are of the same type and both are parallel to each other. So B1 is parallel to B2. So if I draw the planes, so let me draw the plane first. Let's say this is my second plane. Okay. And here I have one dislocation, edge dislocation. Okay. Let's say this is dislocation D1 and this is the direction of Burgess vector. And let's say I have the another dislocation here, that is dislocation D2, and this is the direction of B2. So you can see that B1 is parallel to B2. So how these two will interact with each other? So let me draw again. So here, what will happen? The dislocation 1 will create a step in dislocation 2 in the direction of B1. So let's say this is my B1. So it created step in here in the slim glide plane. Okay. So this is dislocation D2. This is segment S2, and this is direction of Burgess vector B2. Okay. Similarly, the second dislocation D2 will create a step in a dislocation D1 in the direction that of B2. So here, let's say this is my other dislocation D1. So it will create a step inside this one. Okay. This is the direction of my Burgess vector B1. This is my segment S1. This is my dislocation D1. So here you can see that S2 is parallel to B2. So it will have a screw character, and S1 is parallel to B1. So it will again have a screw character. So both the steps will have a screw character. And as this both the steps have not changed their glide plane, so these are nothing but a kings. So it means the steps S1 and S2 found are the kings with a screw orientation. So here in among these four, The only the last option, that is the S1 and S2 are kings with a screw dislocation is there. So this one is correct. Okay. So now moving towards next question. So match the following. So you have some concepts in A and their reason given in B, and you need to match. Like in A section, they have given the different strengthening mechanism, and in B, they have given how the dislocations will interact in that strengthening mechanism. So you need to match A with the B. So please try to answer it, guys. Any guesses, guys? Okay. So the first thing, that is the solid solution strengthening. So we know in solid solution strengthening, there is an interaction between the solute atoms and that of the dislocation, and that will result in the strengthening of the material. So among this, for first one, this is the option. Means for first one, we have second option. Now in strain hardening, so in strain hardening, we know the dislocation will interact with each other, or in the it will create a Lomer Cottrell barrier, and this is how we will get the strengthening effect. So for this the strain hardening, we have the option that dislocation pile up at grain boundary in coercion between matrix and Lomer Cottrell. So here, this is the second option. That is means for second we have fourth. Now, if we see the third, that is the grain size strengthening. So in grain size strengthening, the dislocation will pile up at the grain boundary, and this will give the strengthening effect. So grain size strengthening is this one. Means for third one, we have the first one matching, and the remaining is, that is the dispersion strengthening. So only one option is left, that is the incoherency between the dispersed and matrix. So we have fourth, three. So the only option that is matching this sequence is the second one. So second one is our correct answer. Okay. So now here comes the next question. The three stages of deformation of single crystals are characterized by. So what are the three different stages observed in the single crystal deformation? So I will draw the graph for you, and from that graph you can let's say This is my section 1, section 2 and section 3. So this is my stage 1, stage 2 and stage 3. So let's say this is my gamma and this is my tau. Now try to answer, guys. Now try to answer it, guys. What are the three different deformation stages in the single crystal? Okay, so here in stage 1, you can see that with increase in the strain, there is not no significant change is being observed in the shear stress. It means the dislocations are easily moving in this stage. So this stage 1 is nothing but the easy glide. Okay, so now in second stage, as you can see that with increase in the strength of the material is increasing, and we can see almost linear relationship. So it means the strain hardening is taking place in this stage. So strain hardening. Okay, and in the third stage, we can see that these dislocations will pile up, and due to the pile up stress, if they want to move, they will climb and they will start moving. So there is not significant changes is being observed, and also the dynamical recovery is taking place in this stage. So this one is dynamical recovery. So now if we see among these four options in the sequence, that is easy glide, strain hardening and dynamical recovery, only the first option is correct. Okay. Now coming to our next question. So compute the dislocation density for a copper crystal if it is deformed under a shear stress of 42 megapascal, and they are asking us to assume the Taylor hardening where G is 50 GPa, mu is 0.5 and lattice parameter is given. So, and they are asking us to calculate the dislocation density. So it's very simple, guys. Just try to calculate and tell me the answer. We need to take the help of one more concept. In last 2 weeks also we have solved some questions using that concept. So you need to use that concept here as well in this question. Like in Taylor hardening, we know the equation, that is tau is equal to Gv upon 8 pi 1 minus mu root 2 into root rho. So all the values are given except that of the B. So you need to figure out how to calculate the B, and you will get your answer. So let me write down the given data first. We have been given tau is equal to 42 MPa, G is equal to 50 GPa, nu is equal to 0.5. The lattice constant, lattice parameter is given as 3.621 Armstrong. We have given, we need to find out the dislocation density. Okay. So here we know the Taylor hardening equation, that is tau is equal to GB upon 8 pi 1 minus mu into root 2 into root rho. So they are asking us to calculate the dislocation density. So if I write, we can write it as 8 pi 1 minus nu upon GB into root 2. Okay. And if I take the square, so I will get tau into 8 pi into 1 minus mu upon GB root 2 whole square. So in this equation, we know the value of tau, we know the value of mu, we know the value of G. Only B is not known. So, but they have given here that the copper crystal, and we know the crystal structure of copper is FCC. So they have given as copper. So copper is FCC, and for FCC we have the Burgers vector as of the type A by 2 1 1 0. Yeah. So if we find out the magnitude, so we'll get A by root 2. So if we put this value here, we'll get our answer, that is rho is equal to tau into 8 into pi into 1 minus 0.5 divided by, we know the value of tau, that is, so sorry, I will put directly values, I do this time. So it is 42 into 10 to the power 6 into 8 into pi into 1 minus 0.5 upon, we know the value of G, that is 50 into 10 to the power 9 into, we know the value of B, that is A by root 2, and A is how much? 3.621 into 10 to the power minus 10 divided by root 2 into root 2, its whole square. So this root 2 will get cancelled out, and if we solve this one, we'll get our answer somewhere around 8.5027 into 10 to the power 14 per meter square. So this is our answer. So if we see the values which is close to this value among above 4 options, so only the option 4 is very close to that of our answer. So the fourth one is the correct one. So now moving towards the next question. So the question is like that: the slip plane for the dislocation found via quartal barrier formed by combination of dislocation with Burgers vector A by 2 1 bar 0 1 on 1 1 1 with another dislocation having Burgers vector A by 2 0 1 bar 1 on 1 1 1 bar plane. So they are asking us to the slip plane of Laumer quartal barrier. So please try to answer it, guys. So I will draw the figure for you so that you will easily understand. So let's say this is my 1 1 1 plane and this is my 1 1 1 bar plane. So on this I have one dislocation with a by 2 1 bar 0 1, and here I have another dislocation 2, that is a by 2 0 1 1 bar 1 bar. So they are asking us to find out the slip length for this dislocation. So if we need to find out the dislocation means slip length for this dislocation, we need to know the line vector and Burgers vector. So as this is the Lomer-Cottrell law, so the Burgers vector will be the summation of these two dislocation. Okay, and the line vector will be the cross product of these two planes, 1 1 1 bar, and it is nothing but our line vector. Okay, and we need to find out the Burgers vector as well. So Burgers vector will be nothing but the b1 plus b2. So now you have the value of your line vector and Burgers vector. If you take its cross product, you will get the slip plane. So let's try to find out and tell me the answer. So here we have line vector as 1 1 1 cross 1 1 1 bar. So if we take its cross product, we will get somewhere around 2 bar 2 0. And if we find out the Burgers vector, that is summation of these two, that is a by 2 1 bar 0 1 plus a by 2 0 1 bar 1 bar. So we'll get it as a by 2 1 bar 1 bar 0. So for slip plane is equal to UR cross BR. So if we put, we'll get somewhere around 0 0 2 bar, or it's 0 0 2. So the only option matching with our answer is this last one. So this is the correct answer. Okay. So this is about the finding out the slip plane in case of Lomer-Cottrell barrier. So now here one next question is also on the Lomer-Cottrell barrier. So the question is like that. Lamarck-Cattell barrier involves the dislocation from plane uh, bar 1 and 1 bar. The dislocation on bar 1 and 1 bar 1 plane have Burgess vector B1 and B2 respectively. Which of the following reaction would result in Lamarck-Cattell law? And they are asking us to use the Thomson state triagram. So first we'll find out the whether all of these reactions are energetically favorable or not. So this is how we can simply check whether our the given option among this given option uh, which of the reactions are favorable. So for this case, if we find out, it comes out to be a cube by 3. Sorry, a square by 3. So this is a square by 3. And here also a square by 3, a square by 3 and a square by 3. Now if we check for this one, green one, so we'll get a value somewhere around 9 plus 1 divided by 36. So it is somewhere around 5 square by 18. For second case, we'll get 1 by 9 a square, and here we have 2 by 36, 1 by 18 a square, and here we have 10 by 36. We have 5 by 18 a square. So all these reactions are energetically favorable. So among these, anyone can take place. So now they have given us the plane, that is this plane, that is bar 1 bar and hello. Okay, so here they have given us the plane bar 1 bar and 1 bar. So here we can see that these are these two planes. Okay, and the Burgess vector that they have mentioned, that is the 0 1 bar and 1 0 1. So here we can see that these are the Burgess vector they have given, is it not? So let me write down the Burgess vector first. That is, first I will write a by 2 0 1 bar 1 bar. Okay, So these are the two Burgess vector. These two Shockley partial will form the our this main Burgess vector. So the Shockley partials for this case will be A by 6 1 1 bar 2 bar plus A by 6 1 bar 2 bar 1. Okay, and the second one here for 101, that is A by 2 101 will get A by 6 211 plus A by 6 1 1 bar 2. Okay, so these two reactions will get. Okay, so let's say this is my A, B, C and D, is it not? Okay, so my A can interact with the C and D. Similarly, my B also can interact with the C and D. So this possibility will get. Okay, so now if we find out the Burgess vector, means we already know the Burgess vector for all these cases, and if we find out the line vector, and if we multiply the Burgess vector and line vector, we'll get the slip plane. If the slip plane is other than that of the our slip system in HCC, then that will be the our Lower-Cottrell law. So if we calculate, that is UR vector is nothing but the cross product of planes, that is we have 1 bar 1 1 bar into 1 1 bar 1 bar. So it comes out to be, how much it is coming out? It is coming out to be 2 bar 0, or we can write it as 1 bar 0. Is it not? Okay, so now if we calculate for this all these cases, that is now plane for, if we calculate here, I will write, that is okay, that is option 1. So okay, so plane 1 for 301 bar into 1 bar 0, it comes out to be how much? It comes out to be 1 bar 3 bar. Now this for second case, that is this one 2 bar 0, it's 2 bar 0 into 1 bar 0. So it comes out to be 004 bar. Okay, the third case is P3, that is third case is how much? 1 bar 0 into bar 1 0. So we'll get the plane as 002 bar, and here for P4 we'll get 03 bar 1 with 1 bar 0. So we'll get P4 as 1 bar 3 bar. Okay, so here you can see all this plane all this plane P1, P2, P3 and P4 are other than that over the slip plane in FCC, that is the 111. So all these will form a Lomer Cottrell law. So among these, it means all the options are correct here. Like all can form the Lomer Cottrell law. But if we see the energetically favorable, the option third one, this one is the most energetically favorable. So that's why this is the correct answer. Okay. So now moving towards next question. So the figure below shows the intersection of two dislocation with a line vectors AB and XY cross two orthogonal planes having their Burgers vector parallel to each other. Which of these statements are true with respect to this configuration? So you need to first draw the interaction, how the interaction is taking place between these two dislocation. Then from the steps form, you can find out their character, and this is how you'll get your answer. Okay, first I will here. Okay, let's consider our dislocation AB first. So the AB will interact with the dislocation XY, and XY will create a step in AB in the direction that of B1. So this is the direction of B1. So if I plot, sorry, okay, so till this point it will be the same. Okay, then here B1 will create a step inside it. Okay, and it will again move to this point. So this is our A B dislocation, and this is the direction of Burgers vector. Okay, so now similarly, in case of dislocation XY, the AB will create a steps in XY in the direction that of B2. So let's say this is my dislocation, S dislocation X. Till this point it will be same, and then it will create a steps in the direction that of B1, sorry B2, and will create a dislocation XY, and its direction is also this B. Okay, so now if you see here, the Burgers vector, that is, let me mark it as step 1 and step 2. Okay, if we see the S1, and let's say this is my B1, so we can see that S1 is parallel to B1. It means it has a screw character. And S2 is parallel to B2. It means it also has a screw character. And as these steps are not changing the glide plane, okay, so these are nothing but the kinks. So both are kinks. So the steps formed in this one will be the kinks with the screw character. So if we see here, the jog with edge dislocation, edge orientation is formed. So among these three, the option 2, that is the kink with a screw orientation, is formed in both the case AB and XY. So this will be our correct answer. Okay. Now moving towards next question. So which of the following method is used to remediate strain aging? So the correct option is skin pass rolling. Okay, in the skin pass rolling, we will use it to remediate the strain aging. So here we have next question. So the below figure show the Frank-Reed source of dislocation multiplication, in which the following steps the shear stress required will be maximum. So, and the black spots are immobile. So you need to find out which of these following four images will require the maximum stress. So please try to answer this, guys. It's very simple. If you know the relation between the shear stress and radius, you will get the answer. So we know tau is equal to alpha GB upon R. So if the radius decreases, then the shear stress will increase. Is it not? So among this, if we see, for this case, the R is approximately to infinity. Here R is R is there. Here, okay. So let's say this is distance D. Okay. So in this case also R is greater than D by 2. Okay. Here also, if we consider, if this is a semicircle, if we consider it as a semicircle, say then in this case the R is equal to D by 2, and in this case also R is greater than D by 2. So among these four, the minimum R is for this condition, this third one. So the correct answer will be this semicircle. So radius of curvature will be minimum for semicircle. So that's why our option 3 is correct. So now coming to our next question. Which of the following are the sources of dislocation multiplication? So these questions we have already discussed in the quick recapitulation. You can answer from that. So here, if we come to the quick recapitulation, here. So dislocation multiplication. So you can see that we will get due to the Frank-Reed mechanism. One option is there. Second is the due to the acidance in crystal growth from the melt. We can get. Third one is the homogeneous nucleation of the dislocation, and the stress concentration aid in the dislocation multiplication. Okay. So if we come to this question. Okay. So here they have given all the options. So among this, all are correct. Okay. So this was the our assignment 11. So is there any doubt in any question till this point, guys? So with this question we end today's session here itself. So if anyone has any doubt, so you can ask. So I think no doubts are there. So in next session we'll try to discuss more on the some concept related question from maybe from beginning of week 1 to week 12. So in this way it will help you in solve in your NPTEL exam. Okay. So thank you everyone for attending, and we'll meet in our next and last session for this course. Okay. So we'll meet on next Tuesday. Okay, guys. So see you everyone.